Hello, everyone. Welcome to CSC 230. As I promised you, there are some of the algorithms that we could not finish, so we are going to go through with this video. I hope you understand this algorithm. I record the algorithms differently, then I'll post them separately. Thank you. So the first question we are going to deal with is FP, which is floating point addition or subtraction. So let's start. It gave us this number 0xBFE 00000 minus 0xC0600000. So the first thing we do, as the algorithm says, is that convert to normalized binary. So I'm going to start the BFE00. The binary is going to be 0. Did I say 0? I meant 1. Why my thing is highlighted? Good. BF B is 1011. Okay, let me highlight this. Good. 1011 1111 1110 0000 0000 0000 0000. All right, this is the first number. And so let's see how it is done. As we discussed in class, we can do this in single precision or double precision, but I'm going to do this example in single precision. So as soon as you get this number, the first thing you realize that the first one is your signed bit. So this number is a negative number. And the biased exponent is the next 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to give it a highlight, yellow. Yes. And everything after that is what we call the fraction of the mantissa. I'm going to give it green. So if we take the yellow part, it's 0, 1, 1, 1, 1, 1, 1, 1. And when you convert this to binary, I believe it's going to be 127. So our bias exponent here is going to be 127. I'm color coding it so that it's easier. So our bias exponent is 127. So the thing tells us to convert it to normalized binary. This is binary, but not necessarily normalized. So to convert it to normalized binary, what we want is that we want it in the form of 1 point something times 2 to the power something. So the power is going to be the unbiased exponent. And as I told you in class, biased exponent is the unbiased exponent plus the bias. So if we want an unbiased exponent, we are going to subtract our bias exponent from 127, right? So it's going to be 127, which is the number we have, minus 127, which gives us 0. So our unbiased exponent is 0. Let me highlight this part so that everybody understands it. Cool. So now, how do we convert this to normalized? It's going to be 1 point. The mantissa part is the green part. So that is what our work is going to be. So it's going to be just the green part. Everything after the point is going to be the mantissa or the fraction point. It's going to be 110. In fact, let me just copy the green part. So that it's easier for everybody to understand. So this times 2 times 2 raised to the power 0, because the power is the unbiased exponent, which we've already encountered. Cool. Going to take this part out. All right, so this is the first number that we've converted to. Also, it's a negative number because the first bit was similar to convert the second number. I already have the second number written, so I'm going to write it down here. Just make sure All right, so this is the second number. And if you check the yellow part, it means the bias exponent. Bias exponent is 128. So if you do the unbiased is going to be 128 minus 127. So we're basically going to have negative 1.11 times 2 raised to the power 1, because 128 minus 127 is 1. Mind you, we got this one from, let me write it down here one more time so that no one gets confused. So yes, this is our biased exponent. I can add a lot of zeros to this, but let me do exactly that. So this is the new number. So remember, this is the first one, the 0xBFE, and this is the 0xC066. When you go to the second part of the algorithm, it says we should match to larger exponent. So this one has an exponent of 1. This has an exponent of 0. So we're going to modify the first one so that it has an exponent of 1, because the exponent of 1 is the larger exponent. So we're going to move this. We're going to move the point around in this one, which is going to be negative 0.1110. I think my thing is still in the exponent form. Yeah, it's going to be negative 0.1110 with a lot of zeros, which we don't necessarily need, times 2 to the power 1 now. And remember, this value that we have here is the first number, this guy here. We just wanted to have an exponent of 1 to match the second one here. So I moved the 0 from here to the front, and it increased the exponent of this to 1. So if I need to rewrite it in how it used to be, it's going to be this minus this minus negative 1.110 with a lot of zeros times 2 to the power 1. Now that they match, I can just copy it and bring it here. Okay, so we've matched the larger exponent, but you can see that mathematically speaking, this is exactly equal to the first part plus the second part, right? So I'm going to make it that way so that it's easy for all of us to understand. So instead of minus negative something, we can just make it a plus. Right. Right, and when you go down to this algorithm addition, I'm not going to go through the addition part, but if you do this addition, you're going to get 0.1110. And we do the addition. When you're doing the addition, you drop the 2 to the power 1 because we matched it, right? So now we have exactly this one. And I'm going to normalize this one, which is going to now be equal to 1.110 times 2 raised to the power negative 1. This one here is just a normalized version of the addition of this one and that one. Remember, we kept this aside so that we can have an easy addition. But when we're done with our addition, we need to bring it back. Hope you understand the math. So now I'm going to bring my 2 to the power 1 down here so that it's complete. 2 to the power negative 1 was from normalizing this. 2 to the power 1 was initially the one that was dropped. So basically, if I want to go back to this line, I can make it like this. I can delete this one, right, and put a bracket here. And let's highlight this a different color. This whole thing is probably blue. Yes. Now you do realize that the answer to the one highlighted in blue is here, which is also the same as this part of the code. I mean, this part of the math, right? So this blue one here on the right side here matches the one here, and we just needed to bring the times 2 to the power 1, and we got the times 2 to the power 1. So now the next thing is that since this is times 2 to the power -1 and this is times 2 to the power 1, they're going to cancel out. You're going to subtract you're going to add the exponents, which is going to give -1 plus 1. It's going to give you a 0. I'm going to write how it's going to turn out to be. I'm sorry, this editing thing is not helping a lot. All right, so I'm going to de-highlight this so that we will not be confused. All right, so this is going to turn into 0, or I can just make it -1 plus 1, which is equal to 0. So the answer, when we do all this, including the sign, turns into 1.11 times 2 to the power 0. After this, we need to normalize whatever we are doing. Right now, this is 1.110 times 2 to the power 0. Change this. I don't like this format. So, okay. Now, for purposes of this class, there will be no overflow or underflow for anything that will give you. So you can assume there will be no overflow. In fact, if there's an actual overflow, it will raise a MIPS exception and our operation will be aborted. So we are assuming that there will not be any overflow. Now we need to put the results in the registers. We know the answer we got is a positive number. So if we are putting it in our registers, it's going to be 0. The first bit is 0. Now the second bit is our bias exponent, which is going to be 127, right? Because it's 0 is our exponent plus the bias. So it's going to be 0 plus 127, which is going to be 0, 1, 1, 1, 1, 1, 1, 1. Now, the next part is our mantissa, which is everything after that point. So here is going to be 1, 1, 0. Then we're going to add enough zeros to make it 23. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is our answer as we have put it in our registers. This is the FP addition subtraction. Thank you.